Here's a training example labeled safe. We feed it forward through the network, we're just looking at the safe output node here, and compute the cost. Our goal is to reduce that cost. So how should each weight and bias change? Let's focus on just one weight. How does changing this weight affect the cost? It affects the weighted sum, which affects the activation, which affects the cost. Let's break that down. How does the sum change when we adjust the weight? It's a simple equation. We're only changing this one weight, so everything else stays constant. The sum changes in direct proportion to the input. If the input is 0, changing the weight has no effect. For us, the input is negative 0.40, so the sum changes by negative 0.40 per unit change in the weight. Next, how does the activation change as the sum changes? That depends on the slope of the activation function at that sum. In other words, its derivative. If the sum is very positive or very negative, the slope is near 0, so the activation barely changes. It'll always be a positive number. It's at its max at 0, which is 0.25. For us, it's 0.22. Finally, how does the cost change as the activation changes? That's just the derivative of the node cost function. If the cost is close to 0, the derivative is also near 0. For us, it's negative 0.66. Negative, because increasing the activation lowers the cost for this node. And thanks to the chain rule from calculus, the gradient for this weight at this input is just the product of these three values. How the cost changes with the activation, how the activation changes with the sum, and how the sum changes with the weight. Doing the same for the next weight, we see that the cost and activation derivatives are the same for every weight and bias in this output node. So we'll store their product and multiply it by the input to quickly get the gradient for each weight in this output node. For the bias, we use an input of 1. We do this for all the weights in each output node, and for every training example, and then average the results. This gives us our gradient, the direction and amount we should adjust every weight and bias to reduce the cost. The best part? We only need to pass each training point through the network once per step, instead of once per weight, like we did with finite differences.